This lecture is Introduction to Linked List, Part 2. In Part 1, we learned how variables and arrays are stored in memory and how arrays are inefficient in terms of memory usage. The solution of this is to use a linked list. So let us try to understand linked list data structure and see how it solves Albert's problem. Instead of asking the memory manager for an array, which would be one large block of contiguous memory, we can ask for one unit of data at a time or one element at a time in a separate request. Let's say Albert wants to store these integers in memory. What if he requests memory for one integer at a time? So he asks the memory manager for memory to store 6. The memory manager says, okay, so you need space to store an integer, so you get this block of 4 bytes at address 204. So Albert can store 6 here. Albert makes another request, a separate request for number 5. Let's say he gets this block at address 217 for number 5. Because he makes a separate request, he may or may not get memory adjacent to number 6. Higher probability is that he will not get an adjacent memory location. So similarly, Albert makes separate requests for 4 and 2. And let's say he gets these 2 blocks at address 232 and 242 respectively for numbers 4 and 2. So as you can see, when Albert makes a separate request for each integer, instead of getting one contiguous block of memory, he gets these non-contiguous block of memory. So we need to store some more information here. We need to store some information that this is the first element in the list. We need to link these blocks together somehow. It was easy with an array once we knew the starting address of the array. But here we need to store information that this is the first block and this is the second block and so on. To link these blocks together and store the information that this is the first block in the list, what we can do is store some extra information with each block. So what if we have 2 blocks, something like this? And in one part of the block we can store the data or the value, and in the other part of the block we store the address of the next block. In this example, in the first block, the address part would be 217 and the address of the next block. In the next block that stores 5 would be 232. In the block at address 232, we store the address 242, the address of the next block that stores the number 2. And in block 242, the last block, there is no block after this. In the address part, we can have 0. 0 is an invalid address. 0 can be used to mark the last block at the end of the list. There is no link to the next node or next block. So Albert has to request to the memory manager a block of memory that will store 2 variables. One that will store the value of our element, and one, a pointer variable, that is the address of the next node in the list. In C, he can define the type named node like this that will have 2 fields in the node. One to store data, this field will be an integer, and one more field to store the address of the next block. So Albert will ask for a node of memory from the memory manager. And the memory manager will be like, okay, you need a node that needs 4 bytes of integer variable and 4 bytes for the pointer variable that points to the next node. Pointer variables are typically 4 bytes in a typical architecture. The memory manager gives us a block of 8 bytes, and we'll call this block a node. Notice that the second field in our node structure is node star, which means pointer to node. So this field will only store the address of the next node. So if we store the list like this in memory, as these non-contiguous nodes connected to each other, then we have a linked list data structure. Logical view of this data structure will look something like this. Data stored in these nodes, and each node stores data as well as a link to the next node. Each node kind of points to the next node. The first node is also called the head node. The only information about the list that we keep all of the time is the address of the head node. So the address of the head node gives us access to the complete list. The address of the last node is null or zero, and that means that the last node does not point to anything. Now, if we want to transverse the list, the only way to do it is we start at the head, and then we go to the first node, and we ask the address of the second node, and then we ask the second node the address of the third node, and so on. And this is the only way to access the elements in a linked list. If we want to insert a node in our linked list, let's say we want to add 3 at the end of the list. All we need to do is first create a node independently and separately, and it will get some memory location. So we created this node with value 3. Now all we need to do is fill in the address properly, these links properly, the address of the second particular node to be filled in with this node value 252, and a new node can be address 0 or null. So this is the last node, is not point to anything. Let's show how these nodes are in memory. So I've written the addresses of each node, and I've also filled in the address of each node. Let's say 3 gets address of 252, and this is how it will be in memory and how it will be logically. The linked list is always referenced by the address of the first node, and unlike arrays, we cannot access any of the elements in constant time. In the case of arrays, we use the starting address of the block of memory, and wanting a certain position in the array, we can calculate its position. But in this case, we have to start at the head and then ask the address of the next element, and then ask the address of the next element, and so on. So time taken to access elements is proportional to the size of the list. Let's say the size of the list is n. The worst case, to transverse the list, you must go through all of the elements. So time taken is proportional to n. Or in other words, the time complexity of this operation will be big O of n. Insertion in the list. We can insert an element in the list. We just add a node and adjust the links. Like I say, I want to add 10 at third position in the list. All we need to do is create a node, throw the value 10 in the data part, and something like this. We will adjust the length of the second node to point to the node with the value 10, and this new node will then point to the node of the value 4. To insert, we will also have to transverse the list for a particular position, and so it will be big O of n as well in terms of time complexity. The only thing is that insertion is we do not have to shift the elements like we did in arrays. We had to do it if we wanted to insert something in between two elements. Similarly, to delete something will also be big O of n. So we can see some good things about linked list. There is no extra use of memory, in the sense that some memory is unused. We are using some extra memory to store the addresses, but we also have the benefit of being able to create nodes as when we want, and we're also able to free the nodes as when we want. We do not have to guess the size of the list beforehand like with arrays. Until next time, see you.